Okay, in this video I'm going to talk about how to derive Ceva's theorem from Menelaus theorem. So in the two previous videos I proved the two theorems, so the Ceva's theorem and Menelaus theorem, and the proofs were quite different. So yeah, first, so the theorems seem to be related. So like the statements are kind of similar. So in one case we have a criterion for when three segments connecting the vertices of a triangle with the points on the opposite sides intersect at a single point, like this, using the ratios of the ratios at which the points divide the sides. It can be sides or the extensions of the sides. And so this is the Ceva's theorem. And the Menelaus theorem is a criterion when 3 points on the lines of the sides of a triangle lie at the same line, are collinear. So this is Menelaus theorem. So so the proofs were quite different. So the proof of Ceva's theorem was involving areas. So it was using the areas of triangles, and the proof of the Menelaus theorem was using similar triangles. So they are proved quite differently, but it turns out that we can derive one from the other. So in this video I'm going to show how to derive the Ceva's theorem from the Menelaus theorem. So so like to give the full statement, so A, B, C, D, E, F. Here we have A, B, C, D, E, F, and the condition when these three segments, these three lines intersect at a single point is that BD over DC multiplied by CE over EA multiplied by AF over FB. So in the case of the Ceva's theorem, this must be equal to 1. And in the case of Menelaus theorem, basically the same product of the same ratios, BD over DC multiplied by CE over EA multiplied by AF over FB is equal to -1. So you see the conditions are quite similar. So we want to derive the Ceva's theorem from the Menelaus theorem. So in this direction. So we assume the Menelaus theorem and we want to prove the Ceva's theorem. So so basically and we are going to prove it only in one direction. So like basically we assume that because both the Ceva's theorem and the Menelaus theorem, it's a criterion, so it's if and only if. So the lines intersect at a single point if and only if this product is equal to 1, and the Menelaus theorem, like the lines, the points are collinear if and only if this product is equal to -1. So we are going to prove the Ceva's theorem only in one direction. So like because the opposite is like easily proven using the main direction of the Cheva's theorem itself. So we don't even need the Menelaus theorem in this case. So yeah, so suppose that AD, BE, and FC intersect at a single point, and then we are going to write the Menelaus theorem for two triangles. So A, B, C, T, E, F, and we consider now the triangle, this triangle BEC, and we consider this line AD. So it intersects and we write the Menelaus theorem for this triangle and this line. So the 3 points A, so this denoted by O, A, O, and D, they are collinear. So therefore, by Menelaus theorem, so let's write A, O, D are collinear. Therefore, by Menelaus theorem, so BT over DC multiplied by CA over AE multiplied by EO over OB is equal to -1. And similarly, we write the Menelaus theorem for this triangle, highlighted in blue, and the line, this line, basically, CF. So we write that F FOC are collinear, therefore by Menelaus theorem we get that so let's start from the vertex E, so EO over OB multiplied by let's go clockwise. So starting from B, so BO over OE multiplied by EC over CA multiplied by AF over FB is equal to -1. And so basically now we need to combine these two equalities to obtain what we need for the Cheva's theorem for the original triangle ABC. So notice that, so basically, like when we wrote this to equality, so we introduced this point O that shouldn't be shouldn't be included in the it's not here in the equality for the chaos theorem. There is no point O here in this equality, so we need to get rid basically of this and of this. All other ratios are those that occur in the statement that we need, in the equality that we need. So, but these two, notice that they're almost equal to each other. So here we have EO over OB, and here we have BO over OE. So first notice that we can invert the both vectors in the numerator and denominator, because like when the vector, so recall what this ratio of vectors is. So like it's equal to the ratio of the segments with the sign plus if the vectors are in the same direction, and with the sign minus if it's in the opposite direction. So if we invert both vectors in the numerator and denominator, then the sign would be the same. So we can write that this is equal to actually OE over BO. So we invert both vectors in the numerator and denominator, and this is exactly the inverse of what we have here, right? So from this we can express now that OE over BO vectors is equal to well, it's easier to move it to the other side. So let's move to the right side. So let's move this to the right side. So then we would have BO over OE is the sign minus, right? From this -1 is equal to what is left on the left hand side. So BD over DC multiplied by CA over AE. Okay, so minus BO over AE, or like we can move the minus to the right hand side now. So minus, so this is equal to minus this. And now we simply substitute it to here, rewrite here. So we get now that minus BD over DC CA over AE multiplied by FC over CA multiplied by AF over FB is equal to -1, right? So now we see that minus and minus cancel each other. So we can multiply simply by -1 both sides. And now here we see that CA and CA cancel each other. And what else? Oh, maybe nothing else. So yeah, so now we get only this ratio FC over AE, and what we need is oh, this is not FC, but this is EC. I'm sorry, EC, because this is E. Yeah, so this is EC. So EC over AE, and here we need CE over EA. So we can observe that EC over AE is simply equal to CE over EA. So again, we invert both vectors in the numerator and denominator. We can do this always. So basically, this is this ratio. So now the whole equality, this equality becomes BD. So becomes BD over DC. Multiplied by CE over EA multiplied by AF over FB. This is equal to 1. And this is exactly what we needed. Yeah. So this equality is exactly what is claimed in the Ceva's theorem. So that concludes the proof.